inductor here with, let's say, V of t or VLT, it doesn't matter. So let's say VT, we have a voltage Vs here, we have R, we have a current I. So there is one thing very important. So the idea, if you look at the circuit, so what is going to happen is at some point at t is equal to 0, we will close that switch. So when we close that switch, there will be a step change in the voltage across the terminals of the inductor. Like we will suddenly connect it to a DC source, and then we will analyze how it will behave, how its current or voltage will change. But here there is one thing very important I really want you to keep in mind. Before this circuit, the switch was closed, we may or we may not have an initially stored energy and initially stored current on this inductor. So imagine before we close the switch, there was already, this inductor was already charged, already storing some energy, like maybe it was having an initial current of 1 amperes, right? So when you connect it, so that will of course start with from that initial stored energy. So that is something we should be very careful about. Other than that, we don't have any issues. Okay, so let's try to analyze this circuit. So what happens? So we know before this switch was closed, we know the inductor current was I0. So it has some initially stored. It was having some initial current flowing through it, but again, the idea is that can also be 0. We don't care. So let's try to see how this circuit will behave after, let's say, after we close the switch. So what happens in this case? Let's try to write these circuit equations. So for this case, I can simply write a KVL because I can just sum the voltage around and then I can try to equate it to the supply voltage. So I can say, for example, Vs is equal to, right? And the voltage drop on this resistor will be I times R plus the voltage drop on the inductor will be L times I over dt, right? So that is the general current voltage relationship for the inductor. And since this is the direction of voltage drop, the inductor current is same as I of t direction. So I can just use I. So this is the equation we have. So in this equation, what we are going to solve for is, first of all, is I of t. So we need to calculate the inductor current. That is the important parameter for the inductor. So how we can get the inductor? So this is again a first order differential equation. Like we have I, it's I itself, and then we also have the derivative of I here, right? So that is a first order differential equation. But the difference is from a natural response case, now we have a forced response. Like we have a constant input in the system. If you remember this, solving these type of equations from your math classes, this is the forced case of a first order differential equation. So now let's try to solve for this forced case. It's not really that difficult, just it will require more steps. So the idea is I will try to put any variable related to I onto one side, and then I will take the integral. So that is the general solution case. That was also the approach we did for the natural response. Okay, so let's start to do this as fast as we can. I will take that di over dt to this side, right? That will be equal to 1 over L times, let's do this step by step. So L times di over dt is Vs minus I times R, right? So this is our first step. And then I divide everything to L. So this is my di over dt in this case. So normally if there wasn't any I on the right hand side, I can just take the integral, but unfortunately there is, so I need to take that I to this side as well. So I will try to do some modifications here just to simplify this. So I can take everything into parentheses of just to make it look like something I know, like we have this RL before. So if I divide this thing by R. So we will have Vs minus I think. Oh, sorry, Vs over R minus I. Is this still going correct? Can you just check what we are doing? And then again, just to mimic what we were doing before. So if you remember, we were having minus R over L. So I will do this. I will do another trick here, and I will say this is minus R over L times I minus Vs over R. Just again for simplification and to make it look like the parameters we used before. And then I need to take this I to the left side, and I need to get rid of this dt. So this will be something like di over maybe I minus Vs over R, which is equal to minus R over L times dt. Right? This is so much similar to what we have done before, except this constant, which is really not affecting so much things in the calculations. So let's do the integration. So this will start from the initial current and go to any time that we would like to calculate current. I will replace the variable I here. Dx is equal to x minus Vs over R. And then on the right-hand side, that minus R over L does not depend on the integration. So that will be from 0 to t. And then I will put dy here on the right-hand side. Okay, so what is the integral of this thing? Dx over x minus a constant. We know the integral of ln x, dx over x, right? Which is ln x. So what is the integral of dx over x minus a constant? Yeah, so it says, yeah, a lot of people finds it. U is equal to x minus VSR. They are very similar. Yeah. So the integral here, the result here will be something like ln x minus Vs over R, right? So in this case, if this is ln x minus VR, so we will again evaluate this at IT and I0, right? Okay, and then on the right-hand side, integral of dy is y. So this will basically again be minus R over L times t. So I'm not even going to calculate what is going on in that right-hand side. That will be very, very easy. So in this case, again, I will use the tricks we did before. So this will be ln. So let's do it one by one. I don't want to confuse anyone. So that will be ln IT minus Vs over R minus ln I0 minus Vs over R, right? Which is equal to this. Now I can combine these ln subtraction, which will be something like ln. We are doing basically repeating this very similar things. Vs over R. Now I can take exponentials of both sides so that I can get rid of this ln here. So if I do it, so this left-hand side will be IT minus Vs over R divided by I0 minus Vs over R, which is equal to e to the minus R over L times t. Then I will just calculate I of t from here. That will be very simple. I of t is going to be, so that will be a constant here, Vs over R, plus, so this will be multiplying this number. So that will be I0. Actually, I know I0, which is, let's say, I0 minus Vs over R times e to the minus R over L times t. So this is my solution for the inductor current when you have a forced response, right? So let's look at the effect of those initial conditions. So let me see if there is anything somewhere that I can use. So nothing useful really. So did we calculate the initial current? Yes. So here, for example, we said there was an initial current flowing through this inductor. So I will replace that I0 with capital I0. So this was constant. So this was the initial current flowing through the inductor before we did the step change. And then we have this Vs over R. I will just write it this way so that it looks simpler to us. And I think this is as simple as I can get with this one. But again, of course, I can say tau is equal to L over R, and I can replace this equation with something like Vs over R times, plus I0 minus Vs over R e to the minus T over tau amperes after T is equal to 0. So this is something, this is the best, let's say, this is the simplest case we can go with this. But of course, we can do more modifications if there are something like, for example, we said that initial current flowing through the inductor can be 0. So let's say for I0 is 0, we can make this simpler. So what you're going to see is, so this is Vs over R minus, now we are going to see Vs over R times e to the minus T over tau, right? So now I can put this into parentheses of Vs over R. So that will be I of T is equal to Vs over R, right? 1 minus e to the minus T over tau. This equation you see here now, oops, can't, is extremely important. This is really quite important. So this tells us, intuition, this tells us a lot of things. So let's try to see what is going on here. So at T is equal to 0, this thing is 1. That one is 1, right? E to the minus T over tau at T is equal to 0, this one is 1. So basically what? This thing is 0. Let's see, just to make sure. So at T is equal to 0, this thing is 1. So this one becomes, this thing becomes 1. And the current starts from 0. So at I0, the initial current is 0. Right? Then what happens? We know that initial current was 0 because we assumed it here before doing this derivation. But what happens as T goes to infinity? So as T goes to infinity, this thing here will go to 0, right? So this thing will be 1. So basically, as T goes to infinity, IT will go to Vs over R. Right? Your friend, I think Aaron already wrote this, but let's look at this intuitionally. Let's go back to our circuit oops, I don't know why I can't move this, but very interesting. Oops, there's a small issue with the tablet, but if you remember the circuit while I'm trying to solve this issue here, maybe I can stop sharing for a second. So the issue here is, if you remember, we had a voltage source connected to a resistor plus this inductor. So what happens if you let that circuit run until infinity? So I solve the problem. I hope you can see the screen again. So this was the final equation we calculated. We are saying that at as T goes to infinity, the current will go to Vs over R. And if you go back here, we can try to understand this intuitionally. If we let the circuit run until infinity, how that inductor will behave?
Short circuit.
Yes, inductor is like the wire, it will be short-circuited. And in that case, of course, like if this thing is short-circuited, like if this is short-circuited here, then I know that current is Vs over R, right? So it's something you can calculate very simple. So in this type of problems, we will do this again for a general solution. The initial values and final values are quite important. So you should be immediately responding to those type of questions. So when you see this type of switching systems, you should say, okay, the initial values are this. We calculated like initially they are behaving like this. And at final condition, like that will be short circuit. I can calculate the final value of the current. So you don't even need to do those a lot of those derivations. You should be able to immediately respond to those type of problems. And believe me, we will be using those initial value and final value calculations a lot in our course. Okay, and then in this case, there is one more thing we need to calculate. It's again very simple, but the idea, the questions. I mean, we should also calculate the voltage across the inductor. So we calculated the current here, I of t. And when you have I of t, calculating the inductor voltage is quite simple because we know V of t is L times di over dt, right? So, but which case we should do this? I will use this very general solution. So here we did this for I0 is equal to 0, but this was the general solution, right? So I will use this current. Yeah. Let's say that one, this one is our current. And I need to calculate this thing. So Vt is equal to L times di over dt. And I will just take the derivative of this thing. And then here, this is constant. Its derivative will be 0. So here, this is a constant multiplying this thing. So that constant will remain as constant. So that will be, I will still have it here, Vs over R. And then the derivative of this is going to be what? Minus 1 over tau, right? So that will be minus 1 over tau times e to the minus t over tau. Is this okay for everyone? Let me check if there is any issues. Can you check this calculation? So tau is L over R. So basically this will be, I can just change this with R over L, I think. And of course we can simplify this again, right? It's, I don't know what kind of simplifications we can do, but let me see if there is anything I can do here. Okay, that will simplify. Actually, there are actually many simplifications we can do here. So what I can do is that L will cancel that one, right? So our V of t will be much simpler than this. So we may have, there's a minus here. If I'm and I can divide everything by, multiply everything by R. So that will be R. So if I do minus, it should be something like Vs minus I0 times R times e to the minus t over tau. I think that is volt after t is equal to 0. Is this okay? Let me see. Okay. I think that is correct, but please check the calculations. I wasn't very sure. And then again, it depends on this. A lot of things depend on this initial current. So if that is 0, we will cancel that part and then we'll continue, right? Okay, so that is our derivations for the step response of an RL circuit. But if there is anything you don't feel comfortable, we can try to redrive those parts. But I think up to now it looks okay. I will need a 1 minute break to do something. There are some disadvantages of teaching at home, studying at home. I need to do something for my baby for